You know, artificial intelligence. It can feel like pure magic, right? But what if I told you that under the hood, it's actually built from incredibly simple parts, all working together? In this explainer, we're going to pull back the curtain and look at the real engine that makes it all tick.
I mean, we've all seen it, right? The headlines are everywhere. You've got things like ChatGPT writing entire essays, creating unbelievable images, making these super complex decisions. And all of this power comes from one core technology, something called a neural network.
But that just leads to the big question, doesn't it? How? How does that actually work? How does a machine look at a bunch of data and come up with something that feels, well, intelligent? To really get it, we need to zoom all the way in. I mean, really, really small.
Yeah, we're going to break this whole thing down to its most fundamental piece, its most basic building block, a single artificial neuron.
Okay, now before you get scared off by terms like neurons and networks, just forget all the complex math for a second. Seriously, just think of one neuron as a simple little gatekeeper. That's its whole job. It looks at one piece of information, checks it against one simple rule, and makes one simple decision. Yes or no, on or off. So let's make this super concrete. Imagine YouTube is trying to figure out if it should show you an ad for YouTube Premium. A single neuron could handle this. The input, your age. Let's say you're 17. The rule is simple. Is age 18 or older? For a 17-year-old, that's a no, right? So the neuron outputs a 0. No ad. But the second you turn 18, boom, the rule is met and it outputs a 1. Yes, show the ad. See? That's all it is. A tiny, simple decision.
Now that little rule the neuron uses, it has a fancy name, of course. It's called an activation function. But don't let the term fool you. For what we're talking about right now, it is literally just an on-off switch. If the condition is met, the switch flips on, outputs a 1. If it's not, it stays off, outputs a 0. Simple as that.
Okay, so that's one neuron, one piece of information. But life's a bit more complicated than that, isn't it? What happens when a decision isn't just based on one thing? What if you have, say, 2 inputs?
Let's go back to our YouTube example. What if it's not just your age? What if YouTube also looks at how many hours a day you watch? Now we've got 2 pieces of data. The neuron's job gets a little more interesting. It's not just a simple check anymore. Now its job is to basically draw a line on a chart, a line that separates the people who are likely to subscribe from the ones who probably won't. And that line has a name. It's called the decision boundary.
And here's where it gets really cool, because this is probably going to sound familiar. Remember in high school math, the equation for a line, y equals mx plus b? Well, a neural network is doing the exact same thing. It just uses some different terminology. That m, the slope of the line, in a neural network, that's controlled by something called weights. Think of them like little control dials you can turn to change the angle of the line. And b, the y-intercept, that's called the bias, and it's like a little nudge that moves the entire line up or down. It's the same math, just with a new job.
Okay, so the network has these dials, these weights, and this bias that it can use to draw any line it wants. Which leads us to the biggest, most important question of all. How in the world does it know where to set those dials? How does it find the perfect line?
This right here, this is the secret sauce. This is the heart of what machine learning actually means. Because when a network starts out, it has no idea what it's doing. The settings are basically random. Its first guess, its first line, is almost guaranteed to be terrible. So, how does it learn? How does it get better?
Well, it gets better by getting a score for how wrong it was. It's like a game. Every time the network draws a line and makes a prediction, it checks its answer against the real answer, and it calculates a mistake score. The technical term for this is a loss function, but mistake score is all you need to know. A high score means, wow, you were way off. A low score means, hey, not bad. The entire goal of the network, its only purpose in life, is to get that mistake score as low as it can possibly go. And this whole learning thing happens in a loop, a cycle that just repeats over and over. Step 1, the network makes a guess. This is called feed forward. Step 2, it gets its mistake score using that loss function. Step 3, And this is where the real magic happens. It uses a clever process called backpropagation. This is how it looks backwards from the mistake and figures out which of its little dials were most to blame, and more importantly, which way to turn them to do better next time. And finally, step 4. It makes a tiny adjustment to those dials and starts the whole loop all over again. And again, and again, millions, even billions of times.
There's a really great way to picture this. Imagine the mistake score isn't just a number, but it's a giant hilly landscape. The high peaks are where the mistakes are huge, and the deep valleys are where the mistakes are tiny. The network is basically standing on this landscape blindfolded, and its job is to find the absolute lowest point. So what does it do? It feels the ground at its feet to see which way is downhill. That's the gradient. And it takes one small step in that direction. And it just keeps doing that, step by step, feeling its way downhill. This whole process has a name, and it's a perfect one: gradient descent.
Okay, so this is great. A neuron can learn to draw the perfect straight line. But what happens when the problem is, well, curvier than that? What about problems that a simple straight line just can't solve?
Because let's be honest, the real world is messy. It's complicated. Just look at this data on the screen. There is no way you can draw a single straight line to neatly separate the orange dots from the dark ones. It's impossible. And this is the problem that gives us the deep in deep learning.
So how do we solve it? Well, instead of just an input and an output, we start adding extra layers of neurons in the middle. These are called hidden layers. Now, their job is really interesting. They don't make the final yes or no decision. Their job is to be data transformers. They take that messy data and they stretch it, they twist it, they warp the whole space it lives in. They manipulate it in just the right way so that by the time it gets to the final layer, that complicated, impossible pattern has been untangled into something that, you guessed it, can be separated by a simple, straight line.
And this is where things get truly powerful. Think about a network trying to recognize a face in a photo. The very first hidden layer might just learn to spot simple things, like little diagonal lines or bright and dark edges. But the next layer takes those edges and learns to combine them into corners and curves. And the layer after that combines those into more complex shapes, like an eye or a nose or mouth. Each layer builds on the last, learning more and more abstract concepts, until that final layer can put it all together and say, hey, that's a face.
So, just how deep, how big can this get? Well, a state-of-the-art model like GPT-4 is estimated to have something like 1.8 trillion of those little dials, those weights and biases we talked about. 1.8 trillion. And every single one of them is being carefully tuned using that exact same simple loop. Make a guess, measure how wrong you are, and take a tiny step downhill. It's just happening on an unbelievable scale.
All right, let's take a breath and zoom back out. Let's look at the big picture and bring this whole thing together, from that one little neuron all the way to a massive deep network.
Because when you put all these pieces together, you see the most important thing. A neural network isn't just a giant memorization machine. It doesn't just store answers. It's actually learning a perspective. It's learning how to look at the data. Through all that trial and error, through all those tiny steps downhill, it figures out the perfect series of transformations to take messy, complex, real-world stuff and make it simple enough to understand.
And that leaves us with a pretty wild, almost mind-bending final thought. When you see what modern AI is capable of, all the creativity, the complexity, the things that feel like magic, could it be that all of it, is just what happens when you connect billions of those simple little on-off switches and let them learn from trillions and trillions of tiny mistakes?